never are. So what do we got tonight?
Not a whole lot. We just have a review packet.
Okay. Stuff you can read to me, or do you need to send it to me?
No, I can read it.
Okay.
Just trying to find one. It's polynomial equation with rational coefficients has the given roots. Find two additional roots.
Okay, what are the roots?
2 plus 3i and root 7.
If 2 plus 3i is one solution, what's another?
Negative 2 minus 3i?
No, it's just 2 minus 3i. So, in other words, the conjugate of that is this. Imaginary solutions always come in pairs. So if 2 plus 3i is one solution, 2 minus 3i is another. Irrational solutions always come in pairs. So if root 7 is one solution, what's another?
Negative root 7?
So there's your 4 solutions. Now, do we have to find the polynomial or just all 4 solutions?
Just the solutions.
Okay. To get the polynomial, we would take x minus this times x minus this times x minus this times x minus that. That would give us the 4th degree polynomial.
Okay.
We know it's 4th degree because it has 4 solutions. If one of those solutions was 2 minus root 7, then the other solution is 2 plus root 7.
Okay.
So it's just the conjugate.
What about, it says use the rational root theorem to list all possible rational roots for each polynomial.
Okay?
Then find any actual rational roots, and then verify your roots using some synthetic division.
Okay? Let's do it. Give me a polynomial.
2x to the 4th equals 9x squared minus 4.
How can we do this problem without using the rational root theorem? Couldn't we use substitution and just turn it into a quadratic and solve it that way?
Yeah.
In other words, we have an x to the 4th and an x squared. That's if we let u equal x squared, then what we really have here is 2u squared minus 9u plus 4 equals 0. And we can certainly solve it that way. Okay? They don't want you to solve it that way. They want you to solve it using the rational root theorem, so let's do that. So this is 2x to the 4th plus 9x squared plus 4 equals 0. So what does the rational root theorem say? If there's a rational root, its numerator must be what?
Positive.
One of those factors of the constant. So its numerator has to either be plus or minus 1, plus or minus 4, or plus or minus 2. It's the only possibilities for a numerator. It's the possibilities for a denominator. All factors of that coefficient.
Okay.
Plus or minus 1, plus or minus 2. So all possible fractions are what? In other words, a possible solution would be what? What are my possibilities? In other words, let's take that over that, and then that divided by that, and then that over each one, and so forth and so on. So 1.
1/2.
Okay.
4. 2. And that's it.
Okay. So those are our possible solutions, rational ones. Assuming there are rational solutions, because there don't have to be on this. Because this is a quartic, it could have 2 imaginary and 2 irrational ones. So we don't know that there are rational solutions. But if there is one, it has to be one of these 4 numbers. So let's use synthetic division to test each one. So get me started here.
I'm sorry, what? I was writing.
Okay, we're going to use synthetic division
Okay.
to test each of these solutions and see if we get 0, meaning it is a solution.
Okay.
So the first one I'm going to do, I always do the easiest one, plus 1.
And you'd have
What goes up across the top?
2, 0, 0. No, 2, 0, 9, 0, and 4.
Okay.
Bring on the 2.
No. So we can take away the plus 1 as a possibility. Let's try minus 1. Can take away that. Let's try the fraction last. I'm going to do 2 next. Let's try minus 2. You follow what I'm doing here?
Yeah.
In other words, the moment I see that it's not 0, did I do plus and minus 2?
Yeah.
Okay, let's try 4. Doesn't look like this is going to work. Let's try minus 4. Can you kind of see the advantage of synthetic now as opposed to long division?
Yeah.
I mean, you can do these really fast with synthetic. So we're going to have to do the half. That must be the solution. In other words, I did plus or minus. Did I do minus 4?
Yeah.
Let's try minus a half. None of them work. Okay, so if none of them work, let's go back and see if we can solve this using U substitution and see what the solutions are. What was the problem?
2x to the fourth equals 9x squared minus 4.
But what was the questions they wanted? What they want you to do?
List all possible rational roots.
Okay.
And find any actual roots.
All right. So we didn't find any rational roots. And we tried all the possibilities. So the way to find the roots is we know how to use U substitution. So we're going to let U equal x squared. And we're going to have 2u squared plus 9u plus 4 equals 0. Yeah, that factors easily into u, or 2u plus 1 times u plus 4. Gives you 8u, 9u. So, u equals minus 4 or u equals minus 1/2. I must have made a mistake. No, I didn't. If u equals minus 4, then x equals plus or minus the square root of minus 4, which is 2i. So there's two solutions. Neither one rational. And if u is equal to minus 1/2, then the other solution is plus or minus the square root of minus 1/2, which is square root of 2 over 2i. That's 1 over square root of 2, which is square root of 2 over 2i. So there's two solutions, there's two solutions. None of them were rational. They were all 4 complex. So that's why our rational root theorem didn't find any. She really wanted to torture you to make you try 8 different possibilities. She probably did it just to show you that if you use synthetic division, it can go pretty quickly. Because I did. I tried 8 different solutions, and it only took me maybe 3 or 4 minutes. None of them worked. So here's the 4 complex solutions. That and that. Do you have answers on this one?
No.
Okay. That looks right. Certainly, if u is negative and u is equal to x squared, then all the solutions are going to be imaginary. Because x squared can't be equal to a negative number unless you use imaginary numbers. So, pretty confident with that. Okay. You want to give me another polynomial?
Yeah. Do x cubed minus 5x squared plus 2x plus 8 equals 0.
Now notice that this is a cubic. So it's going to have 3 solutions. So it has to have a rational solution. There's no way it could have just complex or just irrational solutions, because there would have to be an even number of them. So if you know that there's exactly 3 solutions, one of them has to be rational. So the rational root theorem, what are our possible solutions? What else?
We would have 4 and 2.
Okay, so here's 8 more. And this one, we can't use substitution. One doesn't work. No. Minus 1. Have you learned about upper and lower bounds yet?
No.
Okay. This has promise. There's one solution. Minus 1 is a yes. Now, what's the best way to get the other two solutions?
I don't know.
What we have remaining here, that is the remaining quadratic. In other words, one of my factors is x plus 1, and my other is this quadratic, x squared minus 6x plus 8. And let's see, is this imaginary? I think it is. 6 squared is 36 minus 4 times 8 is 32. No, that's going to be real, but irrational. In other words, if we take our solution that we found and divide it into the polynomial, we end up with the quadratic that's left. In other words, with one solution, we can knock a cubic down to a quadratic. If I wanted to, I could manually divide x plus 1 into this polynomial, like this, and I would get x squared minus 6x plus 8. Okay? So, let's figure out the two solutions based on that. Use the quadratic formula. I don't believe it factors very nicely. Oh, yeah, it does. Factors very nicely. Factor that for me.
X minus 4, x minus 2.
So my three solutions are minus 1, plus 4, and plus 2. All real. All rational. Now, maybe she wanted you to go through and use the rational root theorem to find all three of these. But that's kind of silly. That's the hard way to do it. In other words, once you've found one, you know the remaining is a quadratic, and you can factor it or use the quadratic formula, which to me is a lot easier than using that rational root theorem. But notice that all three of these solutions do fit the P over Q. So we could have found all three solutions had we continued to test all 8 possibilities. I think it was just a little faster doing it this way. Once we found one, all right? You get the idea, right?
Yeah.
All right. You want to do another one?
I have a different one. Let's find a third-degree polynomial equation with rational coefficients that has the given numbers as roots.
Okay.
First one's 5 and 2i.
So what's the third root?
That's it.
Well, when they give you one complex root, you know another one automatically. They always come in pairs.
Minus 2i?
Okay, so those are our three roots. So what are our three factors that we're going to multiply together to get this polynomial?
X minus 5, x plus 2i, or x minus 2i.
Multiply your imaginary ones together first. What do you get when you multiply those two together? Notice it's the difference of squares. So this should be, in other words, by difference of squares, I mean our answer is going to be this. When we multiply them together. You see why? Just using the philosophy of difference of squares. In other words, knowing that a squared minus b squared equals a minus b times a plus b. So when you see this, rather than having to multiply it back together, know that it's got to be a squared minus b squared. Well, in our case, a is x, and b is 2i. So I knew it had to be x squared minus 2i squared. Well, x squared minus 2i squared is what? What's 2i squared equal to? Quantity 2i squared. So that becomes x squared minus 4i squared. I squared is minus 1. So this becomes x squared plus 4. Now multiply these two together and you got your polynomial. Go ahead.
The x cubed plus 4x minus 5x squared minus 20.
There it is. Not in the right order, but it's okay. You can put the minus 5x squared second. So whenever they give you the roots and they want the polynomial, just make x minus each root times one another. In other words, usually we go the other way. Usually we get down to something like x minus 5 times x plus 3 equals 0. Well, that means the solutions are x equal 5 or x equal minus 3. We're just going backwards. We're going in reverse when they give you the solutions first. Even though they only gave you 2 solutions, they really gave you 3 solutions. Okay? Got another one like that?
Yeah, it was 7 and I.
Okay? So tell me what to do.
X plus 7, x plus I, and x minus
Now hold
I.
on. If 7 is a solution, then the factor is x minus 7. Right? If we were solving it normally and we got this as a factor, we would set this equal to 0 to come up with x equals 7 is a solution. Therefore, x minus 7 is the linear factor.
It was negative 7 and I.
Excuse me. Excuse me. Because we know if I is a solution, minus I is also a solution. Okay, multiply these two together.
X squared minus I squared.
Like that. Multiply those two together and you got your polynomial. You want to multiply these two together?
Yeah, it's x cubed plus x plus 7x squared plus 7.
There it is. If you were to start with that and try to factor it, you'd eventually get the minus 7 solution. Then you would have this quadratic that produces a plus I and a minus I. Now there is one leap in degree of difficulty that they might throw in here. And that's that they would give you two solutions, and then they would say that the y-intercept is something, which adds another degree of difficulty. But I don't want to get into that if you haven't gotten into those yet. But I suspect you might. Maybe not, but you might. In other words, what was that last polynomial we came up with? Or this one? What is this one, the answer? Do you remember?
X cubed plus...
Here, let me write it out. Plus
7x squared.
7x squared plus
X.
Plus x plus 7?
Yeah.
I can't remember what I was going to... yeah. Okay, so this is a polynomial that fits those solutions, right?
Mm-hmm.
Well, guess what? So is this. In other words, this has exactly the same zeros as this one does. If I set both of these equal to 0 to solve for the zeros, notice that the very first thing I'm going to do is divide everything by 2 and then solve it. So there are an infinite number of polynomials that give you those zeros. So if you wanted a polynomial that had a y-intercept of 14, this is the one. If you want the polynomial that has a y-intercept of 7, that's the one. Both of those polynomials have the same three zeros, minus 7, plus I, and minus I. They are different functions, though. One function, well, suppose they were quadratics. You might have one quadratic like that, and another quadratic like that. Same zeros, but different functions. In other words, if I plot this, it might end up looking like that one if it was a quadratic. If I plot this, it would look like the smaller one. So just because the zeros are the same doesn't mean that the polynomials are the same. Okay? All right. Why don't we call it a session?
Okay.
Okay. Hopefully that helped. see. We don't have one tomorrow night, do we?
Mm-mm.
And Wednesday at 8. I'll see you
Okay.
Wednesday. I'll see you Wednesday at 8.
Okay.
Okay, Silas. Bye-bye.
Yeah.